And the title is Exponential and Logarithmic Functions. Okay. So the first function we look at, or 4.1, we are looking at exponential functions. What do you think a function would be called exponential? Just a wild guess.
The whole thing has a power.
Yes, the exponent is the variable. That's why this is called exponential. The exponent is the variable. So here's how it looks like. F of x equals a raised to x, where a is the base and the variable is the exponent. Is the exponent. Now here's a question before we continue and look at this function. Can I raise a -1 to the third power?
Yes.
-1 times -1 times -1 gives us -1. Can I raise 0 to the fourth power? 0 times 0 times 0 times 0 is?
0.
Can I raise 1 to the fifth power?
Yes.
What do I get? Okay. So for the exponential function, however, we will not be able to, or we will not be allowed to use a base that is negative. We will not be allowed to use a base that is 0. And we will not be allowed to use a base that is 1. And the obvious question is why? So I'm really telling you that little a cannot be a negative number, cannot be 0, it cannot be 1. Or in other words, I'm telling you that a must be a tiny positive number between 0 and 1. And the other option is a can be greater than 0. But this little a, which is the base, cannot be negative, 0, or 1. Obvious question, why? Here's why. These two functions, you will see very shortly, these two functions are inverses of each other. If for this function we allow a base of negative number 0 or 1, we will not be able to define this function. This function will not exist. This is the only reason why we have to exclude negative numbers 0 and 1 from the base, not the domain, right? From the base of this function. Domain can be anything. So let's look at two possibilities. One possibility with f of x, let's say, equals 1/2 to the second power. Does this fit here or not?
Yes.
Yes, because a, the base is 1/2, it fits between 0 and 1. Now, can anyone give us an example of an exponential function that has a base greater than 1?
2.
Excellent, 2 to the x. Perfect. So let's graph both of them. Let's try to understand their properties and what's happening here. And after that, we're going to look at applications with these functions. Okay, so let's start the table. We are looking at the first function, which is f of x equals 1/2 raised to the x power. Every time we're asked to graph a function, we know that we have to start with always with the domain. Absolutely, yes. So what is the domain of this function? In other words, I'm asking you, can I replace this x by a positive number, by negative number 0? Remember, we are not talking about the base. We are talking about the exponent. Can the exponent be 5? Yeah. 1/2 times 1/2 times 1/2, 5 times I can create. What about 0? Can the exponent be 0? When we raise a number to 0, what do we always get?
0.
No. Okay, okay, that's
Oh,
okay.
no, you get the number. You get the number.
No. Let's take a look. Let's take a look so we understand this. This is important. Can you please tell me how much is 10 to the third divided by 10 to the third? You agree that it's 1?
Yeah.
Okay, perfect. So now, forget about this for a moment. I copy the base. What do I do with the exponents?
You got it.
Never when I divide, yes. So 3 minus 3. So this is 10 to which power? So then 10 to 0 equals 1. Any number raised to 0 is 1, not 0 raised to 0. So except when a is 0. So any number raised to 0 except 0. Yes, Steve?
So what is 0 and 0 equal?
Very good question. You have to wait till calculus 1.
No.
That is called an indeterminate case. There are 7 indeterminate cases, and this is one of them.
Okay.
Not undefined, indeterminate. Good. So then coming back to our domain, can I replace x by 0?
No.
Yes. What do I get? What would be the answer? Thank you. Awesome. Can I replace the power x by -3?
Yes.
Yes. What do I have to do when I replace it by -3, for example? 1/2 raised to -3. This is 1 over 1/2 to the 3rd. And obviously I have to flip and I get 8. That's another property that we have to remember. A to -n is 1 over a to the nth power. This is an exponential rule from... Okay, very good. So this is 1 over 2 times 1 over 2 times 1 over 2, which is 1 over 8, and I have to flip it and I get 8. So coming back to our question, let's answer the question finally. What is the domain of the exponential function?
Negative infinity to infinity.
So it will join the group of friendly functions, which means we don't have to worry about it. Which functions we don't have to worry about? We don't have to worry about polynomials ever. Why? Because they are defined everywhere. We don't have to worry about the absolute value. It's defined everywhere. We don't have to worry about exponential, right? But which functions do we have to worry about? Never. They're polynomial functions. They're defined everywhere, right? So which 2 functions we looked at, and we really had to think about the domain. Awesome. And radical. Yes, these 2. These 2 functions have problems. The square root, right? The 4th root, every time the index is even, I have a problem. The quantity under that radical must be greater than or equal to 0. And the same thing with the rational. Awesome. Good. This is a function that we cannot consider polynomial. It's not polynomial, but it's a friendly function. Awesome. So let's plug in some numbers. So when we plug in -2, can you please tell me the y value? I brought candy for you, so if you'd like to help yourself.
Is it 4?
Say it again.
4?
Yes, because we have to, it's 1 over 1/4, and we flip, and it's 4. Good, perfect. So what about -1?
1.
2, very good. Is that me?
No, that was me.
Okay, I'm sorry. Thank you. Okay, so when I plug in 0, again, thank you. When I plug in 1, very good. When I plug in 2, very good, 1/4. Now I need this. When I say this, what am I referring to? What do I need here? What it's called? What is it called? The end behavior. The end behavior. Perfect. So let's figure it out together. 4, 2, 1. Then I have a pi divided by 2 people. Then by 4. Then by 8. Then by 16. Then by 32. Then by 64. Then by 10,000. I have a pi and I want to divide it into 10,000 people. How much will you get?
No.
Of course. Which means y equals 0 is what? Yes, which type? Awesome. So horizontal asymptote at infinity only. Let's go this way. 1, 2, 4, 8, 16, 32, 64, 100,000, 1,000,000, 2,000,000, 10 billion. Where am I going? What? Very good. Awesome. We have never seen this before. This is a function that has an asymptote, a horizontal asymptote only at one end. This was not possible with rational functions. Okay, let's graph the function. It's not a difficult function to work with. You will see. It's not as sophisticated as the rational function is or polynomial. Much simpler than that. Okay, so from left to right, please dictate which ordered pair will I have to plot first. Awesome. Next one. Very good. Awesome. Very good. And from this point on, it gets difficult. That's fine. This is the graph, 1/2 to the x power. Let's list the properties of this function. It has so many. Okay, so let's list the domain again. All the properties, let's put them in one place. Domain. Very good. Range.
Infinity, no, 0 to infinity.
Awesome. X-Intercept.
1, there's 0.
X, you're jumping to Y-Intercept. 0, 1, I agree. X-Intercept. There isn't one. Awesome, thank you. None. Asymptotes. Only y equals 0, horizontal asymptote at infinity. Perfect. Is the function increasing or decreasing on all its domain? Awesome. Is it 1-to-1? By the? Yes, by the horizontal line test. Does it have F inverse?
Yes.
Very good. I know nothing about the inverse. Can I graph it? Of course. And we know how. We know we don't need anything. We don't need to know anything about the inverse. And we don't till the next section. So please give me a couple of ordered pairs, maybe 3 or 4, that will help me graph the inverse function. 4, -2. Is that clear why? That's what the inverse function does. So 4, -2. Perfect. Next ordered pair, please. Awesome. Obviously, this point, where does this point go? It has to be part of the inverse function as well, because at this point, it's like a point that is 1, 1, 2, 2, 3, 3. When I reverse, I still have the same thing. So that's also part of the graph. What else?
1, 0.
You didn't say it. I didn't put it.
1, 0.
Excellent. Okay, one more. Very good. 1/2, 1. And then 1/4, 2. This is the inverse function, although we know nothing about it. Can you just determine for me the domain and range of the inverse function? Although we know nothing about it, we were able to graph it, very exact. But now I would like to determine the domain and range.
Negative infinity to infinity.
Which is?
The domain.
Yes. Look at the graph. The domain is 0 to infinity. The range is everything. Right? What does this mean? As I mentioned, these are the last 2 functions we are going to study in this class, in this semester. So what does this mean? What does this tell us about F inverse? It really says what? It will join which type of functions? The ones that we can trust, the ones that are friendly, or the ones that are not friendly? Friendly means defined on all your numbers. This is not defined on all your numbers. I don't like it. I don't like it. I have to worry about its domain. It's only defined like the square root, but except at 0. The square root is defined at 0. This one is not. So this will join the other 2. the radical with an even index, and a rational function. It's not a friendly function. This one is. The exponential is nice and friendly. The inverse of the exponential is not. It has restrictions. I have to worry about it. It joins the group with radicals with even indices and a rational function. Is that clear? So now we have three functions with problems, if you want to call them problems. Okay? Very good. Moving on. Let's look at the other shape now. So we picked 2 to the x. There are two different shapes for exponential functions. One with a base between 0 and 1, and the other one with a base greater than 1. So let's get our table going. What do you think about the domain? Is the exponential a friendly function? Yes. It will be defined like the other one with a base 1/2 everywhere. So -2, -1, 0, 1, and 2. I don't know if I turn this off. I didn't. You know it's going to ring. Okay. So let's plug in -2 and find the y coordinate, please. 1/4. Very good. 2 raised to -2 is 1/2 squared. Perfect. Perfect. Thank you. When x is -1. Awesome. When x is 0, we cannot forget that, right? 1. When x is 1. When x is 2. Good. Now I need to determine this. What is this? The end behavior. Perfect. Let's go this way now. 1/2, 1, 2, 4, 8, 16, 32, 64, 1. Great. Let's go this way. So this time y equals 0 horizontal asymptote at -infinity only. This is something new. We have never seen this before. We've seen functions with horizontal asymptotes, but the horizontal asymptote was the same on both sides. This one doesn't even have a horizontal asymptote at both. Okay, so let's graph. Okay. So from left to right, what would you tell me to plot? Difficult, but let's say.
0, 1.
Okay, but I still have to show this. Okay, next. Every now and then, students ask me in the middle of the semester, can I still get an A in the class? Can I still get an A in the class? And I say, of course. As long as moving forward, your grade follows an exponential function with a base greater than 1, the answer is yes. If it follows an exponential function with a base less than 1, no. That's my joke for today. Okay, so what can you say about this function? Let's go through the properties. Let's go through the properties and decide what properties are still true. Is this function defined on all real numbers? Good. Does this function have a range 0 to infinity? Yes. Does it have an X-intercept? No. Does it have a Y-intercept? 0, 1. It's a pure exponential function. Does it have a horizontal asymptote? Yes, but not at infinity, but at. So that's the only difference so far. So y equals 0, horizontal asymptote at -infinity only. Is this function increasing or decreasing on all its domain? Very good. F increasing on -infinity to infinity. That's the fastest increase that the function can have. Okay. Is it 1-to-1? 1-to-1 means by the horizontal line test, for each y, there is only one x. Because for this function, if you cut it horizontally, for y equals 4, we will find negative 2 and 2. And that's not 1 to 1.
Okay, so you have
Its inverse will not exist as a function. Okay? So it is 1 to 1. It has an inverse, correct? We know nothing about the inverse, but we can graph it. So let's graph the inverse. Please give me the appropriate points or the pairs so I can graph the inverse. 4, 2.
2, 1,
2, 1.
1, 0,
1, 0.
1 half, negative 1.
Perfect. Now you understand that this, even from the graph, it's clear that this function has problems. It's defined from on 0 to infinity, and it has a vertical asymptote. This function has a horizontal asymptote, but this function has a vertical asymptote. It does not exist to this side. So it's a function with restrictions on the domain. Okay. Now let's look at transformations.
Oh, no.
Yes, we will. Right here, right now. Negative 2 raised to x plus 1 plus 4. So this is no longer a pure exponential function. Can anyone give us the base function that was used? Okay, so negative has nothing to do with 2. We know that. So this is negative 1 multiplied by 2 raised to x plus 1 plus 4. Otherwise, it would have been in parentheses, and it would have been a big trouble. Because we cannot have a base that is a negative number. We know that. It cannot be negative, it cannot be 0, it cannot be 1. So negative 2, negative in front has nothing to do with 2. So which base function I used to come up with this? To the? Very good. The exponential function, pure exponential function, 2 to the x, with a base greater than 1. Awesome. So now, what is the first transformation in order of operations that we have to apply to 2 to the x to build this function slowly? In the order of operations. Yes, I want to decompose this in transformations. In the order of operations.
So,
yes?
X, well, JK, I don't know.
Say it again. No, this is so far out. I can.
The exponent?
The exponent, yes. So what do I write?
X plus 1.
Yes, 2 raised to x plus 1. What does 2 raised to x plus 1 do to 2 to the x? When we change x into x plus 1, it's the same for all functions. This is from 2.5, transformations. Yes, left one. Very good. Number 2. Number 2 is a transformation on number 1 in order of operations. What will be the next one? Oops, I need it here. Not yet. In order of operations, I cannot jump here. Now I will put negative 2 to x plus 1. What does negative outside do? Yes, awesome. Reflect with respect to the x-axis. Awesome. I'm glad you remember that. And then the last step is negative 2 raised to x plus 1 plus 4. What does this do to number 2? Very good. Awesome. Great job. Indeed, up 4. So we are going to graph 2 to the x. It's an increasing function on all its domain, and it crosses the y-axis where again? It's an increasing function on all its domain, and it crosses the y-axis where? 0, 1. Very good. 0, 1. We are talking about 2 to the x first. I have to graph the base function, right? So if we go back to our graphs, we know that all pure exponential functions, no transformations, will cross the y-axis exactly where? When x is 0, y is 1. All exponential functions, pure exponential functions, would do that. So here's the graph of 2 to the x. Then you told me to shift this graph 1 unit to the left, correct?
Yes.
So tell me, where will this point go when I shift the entire graph to the left 1? Negative 1, 1. So this is the new graph. 2 to x plus 1. Perfect. Then you told me to reflect this graph. Well done. Well done. I'm going to reflect this graph. Can you please tell me, where does this point go?
Oh.
Very good. Perfect. So this is negative 2 to x plus 1. Let's stop for a moment and look at these 3 functions that we just graphed. And let's identify the horizontal asymptote one more time. The horizontal asymptote is y equals 0. Awesome. When we shift, when a function has a horizontal asymptote, and we shift it up and down, what happens to the asymptote? Must follow the graph. So then if it, in the initial graphs had y equals 0 as the horizontal asymptote, and now you told me perfectly to shift this graph up 4 units, I have to shift the asymptote first. Where?
4.
Awesome. 1, 2, 3, 4. The new horizontal asymptote is at 4. Correct. Now you can say, why do you graph it all the way? It's only on one side. Because when I graph a function or a line, I cannot just show a little piece of it. I have to show the whole thing. Although on one side it means nothing, but I have to show the entire graph. Okay. So then now please tell me, where do I shift this point? This is my reference point. Where does it go? Up 4. 1, 2, 3, 4. Right here. So here's the graph, the final graph. Final, which is f of x, negative 2 raised to x plus 1 and plus 4. Now here's what I would like to do next with the same graph. I would like to find, now by the way, what is the domain of the final graph? What is the range of the final graph? Exactly. So anything can happen, but not to the pure exponential function with no transformations. The pure exponential function has domain all real numbers and range 0 to infinity. Done. But if we put transformations in it, anything can happen. Look at this. This is not a pure exponential function. It still has domain all real numbers because that's where it's coming from. But this time, the range is negative infinity to 4. Awesome. Okay? So range, negative infinity to 4. So expect anything, but not with a pure exponential function. Now I would like to, let's find the X and Y-Intercepts. When we use transformations, we don't really care. We just want to have a rough graph. But now let's, in addition to that, let's find the X and Y-intercepts. And let's try the Y-intercept first. So let me just rewrite the function here. Negative 2 raised to x plus 1 plus 4. Okay, so if I want to find the Y-intercept, what do I need to do? Which one? When you say set it equal to 0, I have to know what is it. That will be the X-intercepts. We want to determine the Y-intercept.
To change it from x to 0?
Yes, you mean f of 0. So x equals 0 when we find the Y-intercept, correct? Everyone? Okay, so f of 0 is, let's do this together. 0 plus 1. 2 raised to the first power. 2 times negative 1. Negative 2 plus 4. So this is 0, 2. Well, lucky me. I wouldn't have known. It just happens that I hit 0, 2. Okay. I would have gone back and adjust the graph once I have this information. Okay, so now I want to find the x-intercept. How do I find the x-intercept?
Set it equal to 0.
What am I setting equal to? 0? Very good. Awesome. So let's look at -2 raised to x plus 1 plus 4 equals 0. Now I have to step back because I've never seen this before. And I have to think and ask myself, what is it? Because it could be absolute value equation, it could be radical, it could be quadratic in form, it could be linear, it could be absolute value, it could be rational, it could be so many different things. Polynomial, etc., etc., etc. We looked at so many. But what is it? It's none of the above. So then what is it? No, not at all. And definitely not for you. What are we talking about? What kind of function are we talking about now?
Exponential.
So what is it?
Exponential.
It's an exponential equation. It has the variable at the exponent level. There's no absolute value, no square root, and so on and so forth. It must be. Okay. Although we know nothing about exponential equations, what common sense will tell you to do? Or please tell me what I should do. Move forward. Exactly. Common sense told us to move forward. Awesome. Now, common sense will absolutely tell us something else. And you know me. Say it again. By. I cannot do that.
-1.
Multiply or divide by -1. Why?
Get rid of the.
Of course. So 2 raised to x plus 1 equals 4. Of course. I don't need those negatives in there. Good. So now let's look at the left-hand side. What is the base on the left-hand side? 2. Let's look at the right-hand side. By any chance, can I present the right-hand side with the same base? Okay, so I can rewrite 2 raised to x plus 1 equals. Very good. Awesome. I didn't do anything, right? I just changed 4 into 2 squared, which is the same thing. At this point in time, please do not ever consider that we are canceling the base. We can't cancel anything. We are only thinking. Here's how we think. 2 numbers are equal. That's what this says. Left-hand side equals the right-hand side. And they have the same base. What has to happen to their exponents? They must equal. One more time. 2 numbers are equal. They have the same base. Their exponents must be the same. So from here, it's guaranteed that x plus 1 must be 2. Otherwise, the left-hand side will not equal the right-hand side. If this is 15, 2 to the 15th power does not equal 2 squared. If this is 0, 2 to the 0 does not equal 2 squared. So from here, I know that x equals 1.
All right.
So 1, 0 is the ordered pair. I'll go back. This is not exactly in my graph 1, 0, but I'm going to say 1, 0. Oh, you can go back and make some adjustments. Yes, please.
So,
Reggie?
is it wrong if you cancel out the base?
Absolutely wrong.
Because that's how I was taught.
No. You have unteach yourself of that. Please don't. Please don't. This is not what we are doing. You will not be able to. So the problem. It's a very good question, actually. Very good question. Here's why. What will you do in this situation? Nothing. So do not do that. Okay? So please don't do that. We're going to look at these problems in this chapter a little bit later. Very good question. Thank you. Okay, any questions on this?
So if they have the same base, then
If 2 numbers are equal and they have the same base, their exponents must be the same.
so essentially it doesn't.
If they don't have the same base, it's a totally different story. And you have to wait for section 4.4 when they don't have the same base. Any questions so far? Okay, so let's look at a couple of applications with exponential functions so you see where they come into play. So on page, this is in 4.1, and we are on page 475. Let's take a look at 66. In 1986, the explosion at the Chernobyl nuclear power plant in the former Soviet Union sent about 1,000 kilograms of radioactive cesium-137 into the atmosphere. The function f of x equals 1,000 parentheses 0.5, and the power is x divided by 30, describes the amount f of x in kilograms of cesium-137 remaining in Chernobyl x years after 1986. So x equals 0 represents 1986. Even 100 kilograms of cesium-137 remain, even 100 kilograms of cesium-137 remain in the Chernobyl's atmosphere, the area is considered unsafe for human habitation. We're asked to find f of 80 and determine if Chernobyl will be safe for human habitation in the year 2066. If we add to 86, 80, we get 2066. So first of all, let's look at this function and clarify or identify the type of function. Is it rational? Is it absolute value? Is it a square root? What is it? Of course. The variable is the exponent, so it must be exponential. So what are we asked to do is just plug it in. 1,000.5 raised to 80 divided by 30. So let's go to the graphing calculator. No one can do this by hand. So let's put it in. 1,000 in parentheses 0.5, close the parenthesis, caret, and in parentheses, I divided 8 by simplified by 80 by 30. So it's 8 divided by 3, and close the parenthesis. So I got 157 kilograms, 157.49 kilograms of cesium-137 still existing in the atmosphere. What would you tell the children or grandchildren of the people who used to live there before the power plant exploded? You can go back. You cannot go back. So this is one type of application. It's a model. Yes, please, James.
I'm sorry to interrupt. Is that 15,000?
Joseph, I'm sorry.
Is that 15,000 or like what is that? That's okay. Thanks.
Sorry about that. Okay. Another application would be interest compounded continuously and interest compounded n times per year. So compounded interest. That is of two types. Compounded n times per year, and the other option is continuously. Before we look at the formulas, which will be given to you, so you don't have to memorize these two, but before I give you the formulas, I would like to just give you two very, very special exponential functions. Here is one, and here's the other. They are so important that they have their own key in the graphing calculator. So if you look at the graphing calculator, you will see this 10 to the x right here, and you have to activate it with a second right here, and with a second again, e to the x. And this e is so important that it also has its own key alone, just e. Okay. When the base of an exponential function is 10, we call the exponential function common exponential function. When the base is e, We call it natural exponential function. What does this E represent? E was discovered, if you want, by a mathematician by the name of Euler. As a token of respect, other mathematicians considered to denote this number by E. And it is 2.71 and so on and so forth. And you can always look at it if you would like to, or I can show it here. So with second and the division, and you press enter, and it gives you, I don't know, 2, 4, 6, 8, 9 digits, decimal digits. It's an irrational number, like pi, for example. So the reason why it's so widely used, and the reason why this is called natural, is because it comes in nature very frequently with a lot of models. So please keep in mind. And how will these graphs look like? Increasing everywhere or decreasing everywhere? Right, because the base is greater than 1. So both of them, 10 to the x will look like this, closer to the x-axis, the y-axis, and e to the x will look a little bit further away, but the same shape. So now we can come back to the two formulas that, as I said, you do not need to memorize. And I'll explain what they mean.
So the index goes up a little slower.
Because the base is smaller. Yes. The higher the base, the closer or the higher the y value is. Yes. Okay. So I'll explain each and every piece of that formula. So it's A equals P, 1 plus R over N to NT. This
Is that M or N?
N in both cases. So A is the accumulated value. So for example, if we borrow some money, this is the amount that we have to return at the end of the term. If we deposit money, this is the amount of money we get at the end of the term, of whatever. The accumulated value. P is the principal. What we borrow or what we deposit. Little r is the annual interest rate. So A is the accumulated value, P is the principal. Little r is not the radius of a circle, but is the annual interest rate. Little n is the number of times we compound the interest per year. Number of times we compound, we recalculate the interest per year. The number of times we compound the interest per year. And little t is time in years. Okay, so the other formula for the continuous compound interest, as you notice, there is no n. It's continuously recalculated every second. So there is no n. A has the same meaning. P has the same meaning. E, we know what it means. It's Euler's number. R is the same meaning in annual interest rate. And T has the same meaning, which is time in years. So now we're ready to look at an application. Let's say problem 53. Are you okay?
Yeah.
I have some cough drops if you need. So 53 on page 475. Find the accumulated value of an investment of $10,000, and we will identify what each number represents for 5 years at an interest rate 5.5. If the money is compounded semi-annually, quarterly, monthly, and continuously. So what do you think 10,000 represents?
You're starting with.
Yes, so that's the principle. Very good. What do you think 5 years represents? Little t. What do you think 5.5, which I cannot use, it has to be 0.055. We never use percent in anything, really, in any formulas.
Oh.
We use the decimal form. So what is this? Little r, very good. So all these represent n, the number of times the interest is compounded per year. So what does semi-annually represent? What is quarterly? And what is monthly? Very good. So here's what we are going to do. First, we are calculating this, and then this one is a different formula, so we'll have to determine it separately. So the accumulated value is 10,000 multiplied by 1 plus 0.055 divided by x. This is what I'm going to put in the formula, x being n. And the power is nt, or xt, or x times 5, or 5x. So let's go to the graphing calculator. And let's punch in 10,000. The reason I put x is because the calculator doesn't have n. Parentheses, 1 plus 0.055 divided by x. Close the parenthesis, power, and in parentheses, 5x. Now, second and table, what do I plug in first?
2.
Okay, 2, enter. 4, enter. And 12, enter. Now, I would like to really see the numbers that are not rounded. So for the first one, a of 2 will be 13116.51. A of 4 will be 13140.67. 13140.67. And the last one, 13157.04. Now the other one, the interest compounded continuously, will be A equals 10,000 e to RT 0.055 times 5. This is what we are going to put in the graphing calculator. Let's do it. And there is no need for the table this time. You can clear everything. So 10,000 e in parentheses 0.055 multiplied by 5 and close the parentheses. Of course, this will give us the largest amount, 13165.31. These are typical applications with exponential functions in which we are determining the accumulated amount or the amount that we have to return if we get a loan of 10,000 within 5 years. Any questions? Any questions?
Can you leave that up?
Sure.
Thanks.
Yes, it is a lot. However, it's not a difficult function to work with. It's nowhere like a rational function where our head exploded in a way with like asymptotes and domain and this and that. This is not the case. This is a much nicer function. Okay. However, the other one has problems. So for that too, logarithmic
Oh, we're just gonna go right into it.
functions. We already graphed them. We didn't wait till no time to wait. We already have them. We already have their graphs. So here's the notation. The notation looks a little bit sophisticated. It's not. Okay, so f of x equals log base 3, I chose 3 of x. So how do we read this? Log base 3 of x. Now what about, so what is the base here? Perfect. Here's another option. F of x equals log x. And you could say, what about the base? The base is not there. When we don't see a base, when there is no base, the base will be 10. So important, the graphing calculator has a key denoted by log. Right here, log. It's the same key with 10 to the x. They share that same key. Okay, what about the name of this? What do you think the name of this log function would be?
Logarithmic exponent.
Careful, careful. We know what 10 to the x is called. We just said that this name is
Common.
common exponential. What do you think the name of this will be?
Uncommon.
Common log. Very good. So this function is common log function. Here's another example. F of x equals ln x. And you can say, what is this, right? So what would be the base here? I don't see any base. But it's not log, so it cannot be base 10. What do you think the base will be? Exactly. What do you think the name of this function will be? Thank you. Natural log function. Look at it. So important. And it has its special key. It's right here. It's ln. And it shares the key with e to the x. So that's why these two have the same base, right? 10 to the x. Now, this is not the reason, but that's why they are in the same key. 10 to the x and log on the same key. Perfect. Okay. Now, the most important concept in this chapter. This is my opinion. Okay? Very, very important concept. The most important concept, in my opinion, in this chapter is this. Any log equation can be replaced or turned into an exponential. So replaced by or turned into an exponential equation, comma, and vice versa. The most important concept. Moving forward in this chapter, we're going to use this all the time. So any log equation can be replaced or turned into, or replaced by, or turned into an exponential equation, and vice versa. Now in mathematical terms, log in any base of x is y is equivalent to, this is a double equivalency symbol, meaning from here I can go this way, and from here I can go this way. So please follow me for the transformation or changing, not transformation, but changing it or transforming it into from a log to an exponential. So please pay attention. Base raised to this power equals x. Counterclockwise, a raised to y equals x. The most important concept in this chapter. So now, let's take a look at a function, an exponential function.